November 29, 1944, off the coast of Honshu, beneath a moonless sky, a steel city moves through the dark water. Her hull is longer than the Titanic, armored like a battleship, and powered by engines capable of propelling 70,000 tons of warship at 30 knots. She is Shinano, the Imperial Japanese Navy's supercarrier, the largest warship on Earth. Admirals call her unsinkable. At 03:17 a.m., 6 white streaks cross the black water. Minutes later, 4 explosions. By 10 a.m., Shinano is gone. 3,000 men are in the water. Japan's invincible dream has vanished beneath its own flag. What really destroyed her was not luck or weather. It was a new kind of weapon that Japan's engineers never saw coming. An invisible system of sound, mathematics, and engineering that turned the Pacific into a graveyard for giants. But to understand how America sank the world's largest carrier with a single submarine, we need to go back to a time when Japan believed it had engineered the perfect warship. In 1942, Japan stood on top of the Pacific. Its carriers had crippled the U.S. fleet at Pearl Harbor and swept across Southeast Asia with unmatched precision. But that same year at Midway, 4 of those carriers were destroyed in a single day. Akagi, Kaga, Soryu, Hiryu. The defeat was so sudden that Japanese engineers vowed never again to lose ships to fragile flight decks and thin armor. From that vow was born a monument to industrial hubris, a new type of warship that combined the firepower of a battleship with the aviation might of a carrier. Its heart would be the unfinished hull of the battleship Yamato's sister ship. Its name would be Shinano. At Kure Naval Arsenal, workers toiled day and night under air raid sirens and shortages. By mid-1944, Japan was losing the war but not its faith in engineering. Designers added 16-inch armor belts, triple hull layers, and watertight compartments so numerous they believed no torpedo could sink her. She was a floating fortress meant to carry 50 aircraft and resist direct bomb hits. Meanwhile, across the Pacific, American engineers were quietly building a different kind of fortress, not one of steel, but of science. In New London, Connecticut, and at Harvard's Underwater Sound Lab, mathematicians and physicists were turning sound into a weapon. They called it Sonar, a technology that could turn the ocean transparent. By the time Shinano was launched in October 1944, American submarines were no longer blind hunters. They were engineered predators armed with electric torpedoes, hydraulic computers, and acoustic eyes. Japan was about to learn that no amount of armor could protect a ship from physics. The Imperial Japanese Navy's engineers faced a terrifying equation. The bigger a ship became, the harder it was to protect. To defend against torpedoes, they added armor. To carry that armor, they needed more displacement. To move that displacement, they needed larger engines and more fuel. Every solution created a new weakness. Shinano was supposed to break that cycle. Using the Yamato-class blueprint, engineers constructed a double hull with an 18-meter-wide anti-torpedo bulge. Her main armor belt was 16 inches thick around the machinery spaces. She had 2,400 watertight compartments and an air pumping system capable of counter-flooding entire sections within minutes. By theory, she could survive a direct hit from half a dozen torpedoes. But theory and reality diverged under wartime desperation. Japan's factories were crippled by bombing. Skilled welders had been drafted. Steel quality fell. Some of Shinano's bulkheads were never pressure tested. Valve seals were installed without inspection. Her damage control crews had barely trained. Meanwhile, across the ocean, American engineers had solved their own nightmare. The Mark 14 torpedo, the most infamous weapon failure of the early war, was finally reborn as the Mark 18. This new torpedo was electric, leaving no visible wake. It ran straight, true, and silent at 46 knots for over 4,000 yards. Most importantly, its magnetic influence fuse detonated beneath a ship's keel, not against its side. That single change rewrote naval warfare. A torpedo exploding beneath a ship creates a bubble of steam that lifts the hull, then drops it into a vacuum. The result is spinal fracture. A ship snaps in half. Armor is irrelevant. Physics wins. By 1944, American submarines carried 24 of these torpedoes each, controlled by a device so advanced it was called a mechanical brain, the Torpedo Data Computer, or TDC. Inside its brass gears and cams lay the ability to solve moving geometry, bearing, Speed, range, in seconds. The U.S. had turned torpedo firing into applied mathematics. Japan was still building armor. When Shinano left port in November 1944, she carried no air group, no escort air cover, and only 3 destroyers to guard her. Her commander believed speed and armor would be enough. He was sailing straight into the most technologically advanced submarine fleet in the world. USS Archerfish was one of the latest Balau-class submarines, a machine built by engineers who believed in science over superstition. She carried a QHB sonar array, a domed transducer at her bow that sent out sound waves and read their echoes as data. To the trained ears of her operators, each echo revealed the shape, speed, and bearing of a target. Commander Joseph F. Enright, who had once been relieved of command for failing to find a target, now had a second chance. On November 28th, his crew detected a massive contact east of Japan. The echo was so large they first assumed it was a convoy of multiple ships. It was Shinano. For 6 hours they shadowed her from a distance of 12,000 yards, using the QHB's directional bearing indicator to plot her course. Every few minutes the TDC translated that data into numbers: target angle on bow, speed, firing bearing. By 03:15 a.m., Archerfish was in perfect position. Enright ordered, "Fire 1, fire 2, and fire 3. 6 torpedoes left the tubes in sequence, running deep at 46 knots. The soundmen heard the first impact after exactly 2 minutes. A dull thud followed by a low-frequency rumble. Then another. And another. Onboard Shinano, damage control team scrambled. The first hit tore open the port anti-torpedo bulge near frame 220. Water poured in. The second struck near the aviation fuel tanks, spreading volatile gasoline through the bilge. The third and fourth breached the aft machinery spaces. The pumps failed within minutes. Electrical circuits shorted. Doors meant to seal off compartments jammed from warped metal. Untrained crews forgot flood sequence protocols. Below decks, boilers hissed as seawater hit superheated pipes. The sound of a Titan dying. By 05 a.m., Shinano listed 15 degrees to port. By 07 nang, 30 degrees. At 09:55 her engine stopped. At 10:18, she rolled onto her side and slid beneath the surface. Only about 1,400 of her 300 crew survived. The world's largest carrier had been destroyed by a single American submarine using 6 torpedoes and a machine the size of a typewriter. The weapon no one expected was not the torpedo itself. It was the fusion of engineering disciplines, acoustics, mechanics, and mathematics working together in real time. The sinking of Shinano was more than a tactical loss. It was a psychological earthquake. Japan's Navy had poured hundreds of thousands of tons of scarce steel into a ship that never fired a shot. American intelligence didn't even know she existed until after the war. The event was classified for months, but within the U.S. submarine force it became legend, proof that technology could defeat size. By 1945, U.S. submarines accounted for 55% of all Japanese shipping losses, nearly 200 vessels totaling over 5 million tons. The submarine service made up less than 2% of Navy personnel, yet crippled Japan's logistics system and starved its war machine. Each success was a triumph of engineering as much as courage. The Mark 18 torpedo's battery was a sealed electric cell using silver oxide chemistry for steady output at depth. Its gyro was accurate to less than 0.2 degrees. Its depth controller used a bellows sensor compensated for temperature. Every component represented years of testing in labs from Newport to Pasadena. Japan's Navy, meanwhile, had no answer. Its anti-submarine sonar lagged by a full generation. Its destroyers' depth charges could not reach deep-running Balau-class boats. And its industrial base was collapsing. The Japanese survivors of Shinano were interrogated after the war. Many described how they could not even locate the incoming torpedoes. There had been no wake, no noise, no warning. To them, it was as if the ocean itself had turned against them. In a way, it had. The Americans had weaponized it. That realization forced Japan's engineers to confront a terrible truth. They had mastered metallurgy, not modern physics. Their strength was in steel, not in signals. As one captured engineer later admitted, "We built walls, but the Americans built the storm." When the war ended, Shinano became a ghost story whispered among naval architects, the ultimate proof that no ship is unsinkable. For Japan, Her loss marked the death of the super battleship concept. The Imperial Navy had believed that armor could compensate for numerical inferiority. Instead, it learned that technology, especially invisible technology, changes the rules faster than armor can adapt. For America, Shinano's sinking validated a new philosophy of war: dominance through information and precision. The sonar arrays of 1944 evolved into post-war acoustic networks like SOSUS, the sound surveillance system incapable of detecting Soviet submarines across oceans. The analog Torpedo Data Computer inspired early digital fire control systems used in missile guidance during the Cold War. The same mathematics that plotted torpedo trajectories became the foundation for early ballistic targeting algorithms. In the shipyards, the lesson was equally permanent. Redundancy means nothing without reliability. Shinano had hundreds of valves and pumps, yet a single design flaw in her flood control sequencing doomed her. Modern damage control systems now rely on distributed sensors and automated sealing. Direct descendants of failures studied from Shinano's blueprints. In post-war Japan, naval engineers approached ship design with humility. When Japan's maritime self-defense force emerged in the 1950s, its ships prioritized electronics and detection, not armor. The shift from strength to sensing was complete. And yet, even today, Shinano remains a symbol, not of pride, but of overconfidence. Modern navies still live in the shadow of Shinano. Every major warship, from America's Gerald R. Ford-class carriers to Japan's Izumo, traces its design lineage through her lesson. Technology is not just protection, it's prediction. Today's Mark 48 ADCAP torpedoes use active-passive sonar seekers, onboard computers, and fiber optic guidance, but their destructive logic is the same as 1944. Detonate beneath the hull, let physics do the rest. Sonar has evolved into entire acoustic networks capable of tracking submarines thousands of miles away. Artificial intelligence now performs the same role that the Torpedo Data Computer once did, solving moving geometry at lightning speed. And yet, the moral of Shinano's story endures. In war, arrogance disguised as engineering is fatal. When Commander Enright's Archerfish fired that salvo into the dark, he wasn't just launching torpedoes. He was proving that innovation beats intimidation. 70,000 tons of armor couldn't protect Japan's greatest ship, but 6 cylinders of compressed air and a handful of electric motors, guided by mathematics, could rewrite naval history. And that's what really sank Japan's supercarrier. Not luck. Not chance, it's science.